Hello, this is Sameen Fatima. I am a professor in the Department of Computer Science and Engineering in the College of Engineering at Osmania University. Today I am delivering a talk on Bayesian learning. Bayesian learning is a very interesting topic in the course Machine Learning. Now, in this lecture we are talking about Bayesian learning, and this is a topic which is used under classification. The first thing we are going to look at is the Bayes classifier. What is that basically? Then the Bayes theorem, then maximum a posteriori hypothesis, then the naive Bayes classifier. Then we will learn a little bit about text classifiers. Now, let us take a look at what is a Bayes classifier, because we will first set up our goal, what is the problem at hand and what is the problem that we are solving. The problem is very, very simple. We all are aware of the databases which have tables, and tables have attributes and values. Just like that, I am going to show you one table. In this table you have attributes like refund, marital status and taxable income. There is the last column in this table which is cheat. Now, in classification we have different classes, and now we are going to classify this data as to whether the person is going to cheat or the person is not going to cheat. We will look at the three different attributes, namely refund, marital status and taxable income. The refund is if the person is filing income tax returns, and then they can ask for a refund. So, is that person filing for a refund? The second column tells us whether the person is single, married or divorced. This is the marital status of the person. The third column is about the taxable income, whether his income, the taxable income is a certain amount, and that amount is listed in the third column. So, based on these three attributes, refund, marital status and taxable income, we will decide whether the person is going to cheat the income tax office or will not cheat the income tax office. That is basically the decision that we have to make. Now, to do that we have to have some prior data. So, if you look at this table once again carefully, you will find that there are 10 records on the top, and these 10 records are labeled in the sense that the cheat column is filled up. That is, we know that the persons with a particular marital status, a particular taxable income, whether in the past they had cheated or they had not cheated. For example, in the first row, a person applied for refund, yes, that person was single, that person's taxable income was 125K, and this person did not cheat. So, we say no. Okay? So, this way we have data about 10 people who have cheated or who have not cheated, and what were their values for the attributes refund, marital status and taxable income. Now, based on these 10 records, our goal is going to be that we have to classify the last 11th record. In the 11th record, I show you that the refund is no, the marital status is married, the taxable income is 120K. So, essentially the Bayesian classifier will be used to answer this question as to whether this last 11th record will be classified as a record of an individual who will be cheating the department or who will not be cheating the department. To do Bayesian classification, we need to recall the Bayes theorem. Let us quickly look at the Bayes theorem. The goal of the Bayes theorem is that if you are given a particular data instance or a data record, what is the probability that we can classify it under one class or the other. So, we represent that as probability C given D. C is the class, and our class here is cheat or not cheat, two classes, and the data is the data record that we are talking about. So, given the data record, what is the probability that the individual will cheat or will not cheat? That is what we are trying to find out. So, there is a beautiful equation given by the Bayes theorem. Probability of C given D is what we have got to compute, and there is an equation for that. In this equation, we need to compute three things. One, the conditional probability of D given C, that is, we are given the class information, and what is the probability that this is the data item or the data record. We also need the prior probability, probability of the class, that is probability of cheat and probability of no cheat. Then we need a second prior probability, that is, what is the probability of the data instance. So, there are three probabilities we need to compute in order to find out the probability of the class given this particular instance. So, the 11th instance is given to me, and I have to find out the probability that it belongs to the class cheat or it belongs to the class no cheat. So, now you see the equation. On the left side you have this probability, and on the right side you have probability. On the numerator you have probability D given C times probability C, and on the denominator you have probability of D. So, I think this is what is basically the Bayes theorem, which we need to recall if you have seen it before, or if you have not seen it before. It is a very simple equation, and we will go forward and we will solve the problem, that particular data table that I showed you. We will take a look at that, and we will actually fit in the values and solve the problem also. Now, let us see how do we compute the probability that the class cheat is yes given the data instance, and the second probability we need to compute is the probability that the class cheat is no given the data instance. So, we are going to compute two different probabilities, one in favor of cheat, one in favor of no cheat. So, obviously, whichever probability is high, I can say that the particular instance can be classified under that particular class. So, if probability of class cheat is given the data instance is higher than the probability of no cheat given the data instance, then I can assign the class cheat is equal to yes. So, we just saw the beautiful Bayes theorem. Now, we need to apply this Bayes theorem to the problem at hand. What was the problem at hand? The problem at hand was, we are given that 11th data instance, and we want to assign a class to that 11th instance. So, the class could be either cheat yes or cheat no. Now, according to the Bayes theorem, I need to compute two different probabilities. One, probability that the class cheat is yes given the data instance. Two, probability that the class cheat is no given the data instance. So, I can compute these two probabilities using the Bayes theorem. Once I compute these two probabilities, what could we do? We could compare these two values. Whichever probability is the maximum one, I am going to say that we can assign the class with the maximum probability to that particular instance. So, the 11th instance, if you say, for example, that the probability of the class is equal to cheat given the data instance is higher than the probability of class no cheat given the data instance, then I am surely going to assign the class cheat is equal to yes for the last instance, that is the 11th instance. Here this is the two class problem, only two classes are there. The same thing now let us look at mathematically, because math, if you look at it first, somehow you start fearing, but I think it is a very simple proposition in maths also. I think once the example is given to you, understanding this math is pretty easy. This is called as maximum a posteriori hypothesis or the MAP hypothesis. In many learning scenarios, the learner considers a set of classes and is interested in finding the most probable class given the data item or the data instance. So, what we just did, it is represented by an equation. H map is equal to argmax P C given D. Now, this small c belongs to the set of classes. So, this small c could be either cheat is equal to yes, one item in the class, or it could be cheat is equal to no. So, we are just saying the same thing, but we have added in the beginning argmax. So, essentially that is what I was telling you. I was saying that we have to compute two probabilities and take the maximum of that. Okay? The same thing is stated in this beautiful equation, which we call as the MAP hypothesis. We are saying argmax of, for the different classes you compute the probabilities P C given D and take the maximum. That is very simple. Now, in the next line of this equation you find that we have expanded P C given D using the Bayes theorem, right. We just saw the Bayes theorem. If I am going to apply the Bayes theorem for P C given D, now this small c is one particular class. Okay? You can have For each class you are going to do this computation. Now, if I apply the Bayes theorem in the next line, I shall expand this to argmax probability of D given C into probability of C divided by probability of D. So, we have done nothing more than expanding that equation of P C given D using the Bayes theorem. The following line you find that we have dropped out the P D. We just said argmax probability of D given C into P C. Now, why did we drop out the P D? Let us look at that. That is very nice, because we are making a comparison between two probabilities, right. Probability of class being class cheat being yes given D, probability of cheat class being no given D. And for both these probabilities, the denominator is probability D, and that probability D, because it is the same instance we are talking about, the value for probability of D will be the same in both these computations. One for cheat is equal to yes and the other for cheat is equal to no. So, when we are making a comparison of two quantities, and if the denominator is the same, it does not make a difference to decide which is the maximum or which is the minimum, even if I drop out the denominator, right, because it is the same for both cases. So, very quietly I drop the denominator P D and I just compute the numerator, which is probability of D given C times probability of C, and then I find the maximum value for which class we get the maximum value, and that basically is called as the map hypothesis, or we are getting the class information with the highest probability. Now, let us look at a new thing which we call as the naive Bayes classifier. Now, naive Bayes classifier is making some simplifying assumptions. To make our life simple, we always make some assumptions, and sure enough we are doing the same thing here. Let us see what we are doing here. Now, we said that we are given a data record or a data instance and we are assigning a class to that, but let me tell you that the data instance is comprising of some attributes. In our example, we have got 3 attributes, namely refund, marital status, taxable income. So, based on these 3 attributes, I am defining the class, whether they cheat or they do not cheat. Now, the data record that we are talking about all along, probability of C given D, we are saying. So, D, that data record, now has to be expanded a little bit, because the data record comprises of 3 attributes. We will be given 3 different values. As you see in the example in the 11th record, we have given 3 different values, one for each of the 3 attributes. Data record is just not one thing that we are talking about, we are talking about 3 different values, or the probability of C given D should now be expanded. And let us look at this screen, where I am saying that I am further expanding this equation of H map. I have argmax probability of class C I, okay, which maps to our class cheat or class do not cheat. I can be 1 or 2 for us, given the values for each of the attributes A 1 to A n. This is written in general, A 1 to A n. In our case, we have 3 attributes. So, we have to say, given the 3 values for the 3 attributes, what is the probability that the class is cheat is equal to yes or cheat is equal to no. Do you get the point? So, this is what we are trying to do. We are now expanding the data record in terms of the values of the attributes that are given for the data record. Very simple. Okay. So, now what am I going to do? Once again, I am going to use this new expression where I have expanded the data record, and I am going to rewrite the same equation. I will apply the Bayes theorem, and with the help of the Bayes theorem, you will say that this same expression can be written as shown in the second line, probability of the data instance having the attribute values A 1 x and A 2 x and A 3 x and so on and so forth up to A n x, given class C I into probability of C I divided by the probability of the data instance. But now the data instance is comprising of the attribute values for each of the attributes, okay, A 1 x and A 2 x and A 3 x and A n x. So, now you see, in our case we do not have n values, we have 3 attributes. So, it will be probability of having the 3 values against the 3 attributes given the class multiplied by the class probability divided by the data record probability, which is again expanded in terms of the attribute values. Okay? So, this is a simple extension of describing the data record further. Okay? We just saw that the denominator does not make any sense when we are making comparisons, because both the probabilities will have the same denominator. So, I am simply dropping the denominator. This third line of the equation is just retaining the numerator. At this juncture, we are going to make a naive assumption. Now, what is this naive assumption that we are going to talk about? Say we are having three attributes: refund, marital status and taxable income. I am making a simple assumption these attributes are independent of each other. Now, this is a simplifying assumption. They may or may not be, but according to naive Bayes, we are able to do this assumption, and we are applying that same assumption here. By doing so, what we can do? We can break this down, this equation. If I am saying probability of refund value being something and probability of marital status being something and probability of taxable income being something, given the class is equal to cheat, I can expand this if they are all independent as probability of refund given something, probability of refund value being something given the class is cheat, into probability of marital status given class is equal to cheat, into probability of taxable income equal to something given cheat is equal to yes. Okay, we just saw the beautiful Bayes theorem. Now, we need to apply this Bayes theorem to solve our problem. Now, we have two classes here. One is cheat is equal to yes, second is cheat is equal to no. Now, we have to compute two different probabilities. One is probability cheat is equal to yes given the data instance, and two, probability cheat is equal to no given the data instance. Now, if I compute these two probabilities and see which of these two probabilities are higher or the maximum, we can say that that particular instance belongs to that particular class. Very simple idea. So, take the maximum of the two probabilities, one for no, one for yes, given the data instance, and whichever turns out to be larger or the maximum, you say that that particular instance belongs to that particular class. That is the basic idea. Now, for this, mathematicians or statisticians, they give it a beautiful name. They call it as a posteriori hypothesis or the MAP hypothesis. Let us look at this equation for maximum a posteriori hypothesis. In our example, in our set of classes, we have two members. One is cheat is equal to yes and the other member is cheat is equal to no. So, for us I can be 1 and 2, that is two members of the set C. Okay? So, what we are saying is you get the maximum of the two probabilities. In our case 2, it could range, if there are more classes, it could range from 1 to n also. So, whatever the I value could be. So, the first line is pretty simple, it is the same idea, it is argmax probability of C I given D that we are talking about. In the next line you will see that I am quietly expanding this particular probability using the Bayes theorem. Okay? We just saw the Bayes theorem, and I can rewrite probability of C I given D as probability of D given C I times probability of C I divided by probability of D. It is a simple application of Bayes theorem. Now, when we expand this using the Bayes theorem, we have a numerator and we have a denominator. Now, when I am computing the probabilities for each of the classes, probability of D given C I, now C I could be C 1, C 2, C 3, you can have different classes. So, probability of D given C I will be computed, probability of C I will be computed, and probability D will be computed. Now, the data instance will be the same 11th data instance, but we are trying to see whether it fits into class C 1 or class C 2 or class C 3. So, basically the numerator values are going to be different for every class, but the denominator, what happens? The numerator is going to be different, but the denominator is what? Probability of D. What is probability of D? Probability of the data instance. And for class cheat is equal to yes or class cheat is equal to no, we are referring to that one single data instance. Okay? So, the probability of D will be the same even for the class cheat is equal to yes, and if we are computing probabilities for the class cheat is equal to no, still the probability of D will be the same, because we are talking about the same data instance. So, when we are making a comparison between probabilities and we are seeing whichever is the maximum, we will take that, then we do not need to compute the denominator basically, because it is the same, it does not make a difference. So, I can quietly drop the denominator and I can retain the numerator, and that is sufficient for me to find out the maximum. So, what I have done here is in the third line I have taken just the numerator probability of D given C I into probability of C I, okay? Because PD really does not make any effect on the comparison between the two different classes in our example. The classes can be more than 2 also in general. Now, we are going to do one more small thing in the naive Bayes classifier. Till now we were referring to the data record as D, okay, the capital D. Now, what I will do is this data record comprises of different attributes, and each attribute has got a value against it. Okay. What are the 3 attributes we had in our example? It was refund, marital status and taxable income. So, my data record is nothing but the 3 different values for these 3 different attributes. So, now what I am going to do is I am going to expand that D and say that it is a conjunction of the value for attribute 1, value for attribute 2, followed by value of attribute 3 and so on up to value of attribute n, a n in general, and in particular for my thing it would be value of refund, value of marital status and value of taxable income, right. When I am talking about the data record, I am doing nothing now but I am talking very specifically. I am saying this data record is now being expressed in terms of the attributes that it comprises of. Okay? That is simply what I am saying. So, once again I will go back to my equation of H map, and in H map we had argmax probability of C I given D, and I will rewrite this equation as probability of C I given value of A1 attribute, comma value of A2, comma value of A3 and so on up to value of A(n). Now, to compute this as we did in the last slide, we will expand it using the Bayes theorem. We will rewrite this again as argmax probability of value A1, comma value A2, comma values A3 up to value A(n) given C I times probability of C I divided by the probability of value of A1 and value of A2 and value of A3 and value of A(n) in the denominator. Okay. These are the very same things we saw in the last slide. I have just expanded my data record, nothing more. At this juncture, I am going to make a very simplifying assumption, or what we call as a naive assumption. Okay. It is a very innocent assumption that we are making. What is the assumption we are making? We are having 3 attributes: refund, marital status and taxable income in our example. We are saying that these 3 attributes are conditionally independent. Now, if I am making this assumption, I can write probability of value of A1 and value of A2 and value of A(n) given C I as probability of value A1 given C I into probability of value of A2 given C I into probability of value of A3 given C I and so on and so forth up to probability of value of A1 n given C I, right. I can individually compute these probabilities for each of the attributes just because of our naive assumption. And what was that? That all the attributes are independent. Got it? So, it is a very beautiful assumption, and now it has made our calculation much easier, making our life much easier. Okay. Now, remember, in these systems we do not get 100% correct results. Our classifier cannot be 100% accurate, maybe it is a little bit plus or minus, maybe 80%, 90%, whatever, but we are able to classify a majority of the records correctly. So, our accuracy should be very good, we should be accurate to a larger number, okay, like 80, 90, maybe 95, something like that. But remember that these are all probabilities, they are all some uncertainty is there, and then we are trying to guess and see if our guess is going to be right or wrong. Okay? And the guess should be done in a very intelligent way. So, what we have done here is we have made this simplifying assumption and we have made our life simple, and now we are just going to compute the product of all these things. What are the product? Product of value of A1 given Ci into probability of A2, value of A2 given Ci, and so on and so forth. So, I have written that product symbol there and I have put probability of value of Aj given Ci. Okay. And now j could range over whatever number of attributes you have, and of course, there is one more term to it, which is probability of Ci. So, we are still retaining that term in the last line, probability of Ci and product of probability of value of Aj given class Ci. This is the final equation that we get if we are adopting naive Bayes classifier. The theory is over. Okay. Let us go back to our example which we saw in the first slide, the table, okay. And let us start applying this whatever math we have learned or statistics or probability that we have learned on this particular table. Look at this slide. We need to classify the record, 11th record, wherein the refund is no, the marital status is married, and the taxable income is 120K. Let us represent this whole record as X, call this record as X because it is very elaborate big one, we will just call it as X. X is equal to this whole record. Now, what is the probability cheat is equal to yes given X, and what is the probability of cheat is equal to no given X? We need to compute these two probabilities. Now, to compute these two probabilities, what do we need to compute? We just saw that equation, naive Bayes classifier. We need to compute probability of X given cheat is equal to yes and probability of X given cheat is equal to no. Okay? And separately we need to compute the probability of cheat is equal to no and probability of cheat is equal to yes. So, let us do that. Okay. Let us calculate probability of X given cheat is equal to no, say first. Now, applying that naive Bayes equation that we just got in the last slide, I can rewrite this probability of X given cheat is equal to no as probability of refund is equal to no given cheat is equal to no into probability of marital status is equal to married and cheat is equal to no into probability of taxable income is equal to 120K given cheat is equal to no. Got this? So, it is a product of these three terms because of the naive assumption, remember that. Okay? Now, what is the probability of refund is equal to no given cheat is equal to no? To compute this, we will look at our 10 records, and in those 10 records we will see only those records where cheat is equal to no. Okay? So, the first record cheat is equal to no, second is no, third is no, fourth is no, then sixth is no, seventh is no, and ninth is no. Okay? So, we are going to look at only these records where cheat is equal to no, and in all these records let us see how many times refund also happens to be no. Okay? So, when cheat is equal to no and refund is equal to no, let us see in the first record that is not the case. Okay? In the second record cheat is no and refund is also no. In the third record cheat is no and refund is no. Then in the sixth record cheat is no and refund is no. Then you have in the ninth record cheat is no and refund is no. So, we have basically 4 records, okay? 4 records in all these no records, cheat no records. Okay? So, there were 7 records with cheat is equal to no, out of which 4 are favoring the case of refund is equal to no. Okay? So, probability of refund is equal to no given cheat is equal to no is nothing but 4 by 7. You can compute in the same way probability of marital status is equal to married given cheat is equal to no and probability of taxable income is equal to 120K given cheat is equal to no. So, these are going to be 4 by 7, 4 by 7 and 1 by 7. So, you see this beautiful calculation there 4 by 7 times 4 by 7 times 1 by 7, which is nothing but 16 by 343. Got this? Now, we have to compute also for cheat is equal to yes. So, let us go forward. Probability of X given cheat is equal to yes can be represented as probability of refund is equal to no given cheat is equal to yes, probability of marital status is equal to married given cheat is equal to yes, probability of taxable income is equal to 120k, given cheat is equal to yes. So, just like we did in the previous thing, we are going to do this with cheat is equal to yes. So, again go back to the table and look at the records where cheat is equal to yes. How many records are there? There are 3 records where cheat is equal to yes. So, we will look at those 3 records. Which are those 3 records? Record 5, record 8 and record 10. Okay. Now, once again let us see if refund is equal to no in these 3 records. Okay. So, if I see record 5, cheat is yes and refund is no. 8th record, cheat is yes and refund is no. 10th record, cheat is yes and refund is no. That means 3 by 3. So, the probability of this is 3 by 3, which is nothing but 1. Now, on the contrary, now if I check for probability of marital status is equal to married given cheat is equal to yes, of these 3 records 5, 8 and 10, nowhere I am finding that the marital status is married, which means this probability turns out to be 0. Okay. Similarly, if you look for taxable income is equal to 120k given cheat is equal to yes, you will find that the probability is once again 0. So, if you look at this, the calculation is 1 times 0, which happens to be 0. Now, which of these, now we have got 2 of these probabilities, there are 2 more probabilities we need to compute. What are those probabilities? One is probability of cheat is equal to no, the other is probability of cheat is equal to yes. The probability of cheat is equal to no is how many times cheat is no in our database or our data table? 7 records are favoring no. So, it is 7 out of 10 records. So, probability of cheat is equal to no is 7 by 10. Similarly, probability of cheat is equal to yes. How many records are having yes as cheat? 3 records. So, that is 3 out of 10. So, probability cheat yes is 3 on 10. Now, going back to what we were looking for, we were looking at the product probability of x given cheat is equal to no into probability of cheat is equal to no. Now, if I compute this, okay, what do I get here? Probability of x given cheat is equal to no is 16 by 343 and probability of cheat is equal to no is 7 by 10. Okay. So, you take the product of these two. For the other class, we have probability of x given cheat is equal to yes into probability of cheat is equal to yes. Now, here probability of x given cheat is equal to yes has turned out to be 0. Okay. So, this whole term goes to 0. Okay. So, now we have seen that the probability of x given cheat is equal to no into probability of cheat is equal to no is greater than probability of x given cheat is equal to yes into probability of cheat is equal to yes, or essentially we are saying that probability that cheat is equal to no given this x data record is greater than the probability of cheat is equal to yes given this data record x. Hence, we can conclude that this x record belongs to the class cheat is equal to no. So, now we have solved our problem. We started with the problem that we needed to assign a class to the 11th record and we have done that. We have assigned a class cheat is equal to no to the 11th record. So, problem solved. Now, let us summarize whatever we learnt in this particular talk. We learnt about Bayesian learning, which is one of the supervised learning methods. In supervised learning, what do we have? We have a training data set available to us in which we have the data as well as a label or a class label in particular along with the data. So, we were given the data and the class information. Using this and using the beautiful Bayes theorem, we tried to classify a new record which came into one of the classes. So, for doing this, we took the help of Bayes theorem. Then we also saw that maximally probably this particular data record belongs to which class. So, that is the second thing we saw. Later again, we went and we made a very simplifying assumption of independence between the attributes of the data, which was called as the naive Bayes assumption. We used that assumption and again simplified the equation that we had. Using all these 3 things, we solved the problem of assigning a class to a new record based on the available data. Now, this has a lot of applications. It also has applications in classifying your email as spam or ham, and many more applications.